To start with, I will talk about the second part of this course, that is the integration of DC microgrid. But before going to the integration part, we will learn about the overview of microgrid and sizing analysis of energy storage system. So, in my today's lecture, this session, I will be talking about the what is a microgrid, the main classification of microgrid, the basic components of a microgrid. Then in the second part, I will talk about the what is the energy storage system and how it is required in microgrid, and with one example, the sizing analysis of energy storage system. So, in other classes, we will be talking about the power electronics part. So, today we are just the basics I will discuss, which you may be acquainted with, but I thought I will start with this. So, as of nowadays this microgrid is getting very much attention, and to define a microgrid, microgrid is nothing but a cluster of renewable energy sources, energy storage systems, load, various power electronics converter which operate bidirectionally when it is connected to grid. And this so here it can operate in a either islanded mode or it can also operate in a grid connected mode. So, this the definition I have mentioned here, the microgrid is a cluster of multiple renewable energy sources. So, that is for a microgrid which contains only renewable energy sources, but there is a possibility of the fossil fuel based microgrid also. So, this is the layout I have shown here. This is the combination of the renewable energy sources as well as the fossil fuel based, that is the combined heat power based microgrid. So, along with the renewable source, the sources are here, and the storage, the load and the generator, means the components of the microgrid, each one by one I will be discussing. But it can, the one point I have mentioned here, the microgrid can operate in either in a standalone mode or it can be operated in a grid connected mode. So, this is what, so but then I will talk about the advantages of microgrid. So, coming to the advantages, so this is basically I am talking about the renewable energy based. Due to the renewable energy source integration, it gives higher efficiency, higher reliability as well as reduced carbon emissions and reduced per unit cost of energy. So, these are the major advantages for which we are now moving from the fossil based system to the renewable energy based microgrid systems. Okay. So, but so this is about the microgrid. It's then we will talk about the classification, how we will classify. So, before going to the total layout of the microgrid based on the different parameters, but means when initially we will try to talk about the what are the different types, means broadly how you classify microgrid or based on which parameter you are classifying it. So, instantly we will say ki based on the power supply, whether it is there is a AC bus, it is connected to AC bus, then it is called AC microgrid. If it is connected to a DC bus only, then it is a DC microgrid, and if it is a combination of AC as well as DC bus system, it is the hybrid AC DC microgrid. So, this is about the configuration of a microgrid when instantly we are talking about. So, coming to the configuration, here in this diagram I have just shown the this again renewable energy based. I am not talking about the fossil based microgrid. So, all the sources here shown here are the renewable energy sources, but the sources are not, means I have not talked about in any of the figure. If you will see, I have not shown the this mini hydro power plant based, because till now as of now what I know, in India in normal scenario this microgrid is not, means in few places available, but mostly we are going for the mostly used renewable energy sources are the PV and wind, which are already available. And here if you see another source I have mentioned here, that is a fuel cell based source. So, that is the upcoming one which will come in few days, but so that is why I have made it dotted. Till now in the existing microgrids, fuel cell is not available. It is still in the research state, and it is it is not very cost competitive. So, here first one, this figure shows the AC microgrid. So, all the sources as well as storage. So, what is the role of storage will go next. but the sources storage are connected to the AC bus through its corresponding power electronics converter, and then the load for the AC bus based microgrid means AC microgrid. If the load is AC, so we do not need any power electronics converter, it is directly supplying to the AC load. But if you are supplying to a DC load, then we need another converter, power electronics converter. So, for there is a corresponding conversion from AC to DC, and the in present state the upcoming load or the already existing this EV is going to a very large, it is going to a means existing load. So, which need a charging EV charging station. So, which is also mentioned for all the type of microgrids here. So, for this again the role of power electronics I am not going to discuss, I am just discussing the based on the type of power supply we are dividing the microgrid into different types. So, here first figure shows the AC microgrid which is connected to the AC bus, then coming to the DC microgrid which is all the sources, the PV and wind sources, the fuel cell and the storage battery is connected to the DC bus with through the corresponding power electronics converter. So, what will be the role of this power electronics converter? Here I am just including it as a black box, and whether it is a if it is connected to the DC bus and the source is suppose PV. So, output is DC. So, we are choosing a DC to DC power electronics converter. If the source is AC giving AC output, that is wind turbine. So, to connect to a DC bus we are choosing AC to DC power electronics converter, whereas here in AC bus system if you will see here the output is AC and we are connecting to AC, again we are using a back to back AC to DC, again DC to AC converter, because of the fluctuating nature of the this renewable energy sources, means wind and solar all are intermittent in nature. So, and then comes the we will talk about the what is the role of storage. So, this is the AC microgrid and DC microgrid, and correspondingly both can operate in the grid connected mode here, but when the DC microgrid is connected to grid, it is through another power electronics converter, that is DC to AC converter. And again, but here it is just the reverse, when I am supplying AC load in AC bus system, I do not need any power electronics, it is directly supplying. Similar is the case when I am supplying a DC load in case of DC microgrid, it is directly supplying the load, but when I am supplying to the AC load, I need another power electronics converter, that is the inverter, DC to AC. So, and each of the system in as of now the power system is AC systems, and now we are going towards this DC again, and each of the system is having its own advantages and disadvantages, and we will discuss that also. So, when we will use the advantage of both the systems, that is AC microgrid and DC microgrid, we will combine the advantages and to form a hybrid AC DC microgrid system. So, this is if you will see, this is just the combination of both the microgrid, AC microgrid, and but the advantage here is we are taking, obviously we are able to use the DC sources and the AC sources, and correspondingly we are connecting to the corresponding buses through the corresponding choosing the proper power electronics converter. What will be the role of the power electronics converter, what are the configurations, topologies, that will be discussed in future classes, not today. I am just showing the type of depending on the type of supply, you have to choose the corresponding power electronics converters. But when we are going for a we are getting more advantages here, we are combining the advantages of AC and DC microgrid, but as we are adding up two things, the system becomes complex due to the integration of both the AC as well as DC systems. So, this is the basic types or classification or the configuration of the microgrid. Then based on the different parameters, so based on the different parameters I have mentioned, so one by one I will tell about the parameters. So, based on the control, the microgrid can be a centralized type when a central controller makes the complete decision, So, coordination and the maintenance here is easy, and it gives a better means output, or it gives a better efficiency. However, if there is a single point of failure, means if it is a centralized based system, centralized based microgrid, but if there is a common point failure, then entire system fails. That is the main limitation. Also it gives a limited scalability and reduced flexibility. So, that are the major drawbacks of these centralized based microgrid systems. But when we are going for a decentralized based control, so that means each components can be controlled independently. So, they are independent of each other. So, in that case it gives a better control. So, it can be we need multiple controllers. So, efficiency means of operation is better, but it gives it needs a complex design, and it is also complex to install and to operate. So, that is why that is complex. If you see means operation wise, the centralized type is easier, whereas the decentralized type gives a more complex operation and complex design. So, this is about the based on the control type of control. And then coming to the type of means the microgrid based on the power rating or the size. So, there are 3 types, one is small, medium and large. How we will categorize this small? So, if the power rating of the microgrid is less than 10 kilowatt, then we will say it is coming under the small size microgrids, and if the power rating is between 10 kilowatt to less than 1 megawatt, then it is falling under the medium size microgrid, and if it is greater than 1 megawatt, then it is falling under large size microgrids. Okay. So, this is based on the size or the power rating wise we are differentiating different type of microgrid. Then already this I have discussed, that is based on the power supply system, we have AC, DC or hybrid microgrid. Then the another parameter is the type of source. So, source can be already I have mentioned, it can be consists of fossil based source or renewable energy based source. Okay. So, fossil based source we are not discussing much here, because we are mainly focusing on the renewable energy based source. So, and when we are combining the both, means we have the mixture of fossil based and renewable energy based microgrid, it is called the hybrid microgrid, means hybrid system having different sources, both fossil sources as well as the renewable energy sources. And under under renewable we have the renewable energy sources that is already known to you: solar, wind, biomass, mini hydro, or it can be micro hydro, both are they are synonymous to each other, and the combination of 2 or it can be more than 2 also, it is called the hybrid renewable energy based system microgrid. Okay. So, there is a possibility of you can have solar wind, you can have wind biomass, or all the combinations together. But when you are going on adding the renewable energy sources, you are increasing, so complexity is also correspondingly increasing, but it is possible. So, but nowadays we are the sources having solar and wind, we are mainly working on these 2 complementary sources. So, forming the PV and wind based hybrid microgrid systems. So, this is about based on the type of sources. Okay. Then based on the type of load, so whether the microgrid is supplying to a residential load or it is supplying to a industrial load or the commercial load, we have 3 types of loading conditions, means the microgrid can be. And the next one is the location based. So, it can be supplying to the microgrid can be located in the at the remote locations, that is the for the off grid operations also we can have this microgrids, or it can be for located at urban areas. So, that is also possible. And the last one is the based on the application. So, if the microgrid is for a military application, we can have different applications mentioned here. military, campus based applications, the communities, and for the districts or the islands. So, these are the based on the applications we are dividing the microgrids into these many types. So, this is the whole configuration, means the classifications of the microgrid based on the different parameters. Then again coming back to the components which I have shown in my first slide, that is for a renewable energy based microgrid. And so, the major 4 components again to clarify it. So, 4 components are the source, the load, then the storage. What is the role of storage, then I will come to that. So, this renewable energy source, the load, the storage. So, storage are the what are the types. Here I have only shown 2 storages, that is the electrochemical storage, that is battery and supercapacitor, and sources I have shown just as a example. Other are possibilities, not that the other sources I have not shown here, but it is existing. Already I have mentioned the other sources of renewable energy, and the load can be the residential or domestic type, or it is industrial or commercial type. So, each unit or each component is connected through the to the bus through a corresponding power electronics converter. So, what are the types of power electronics converter possible? So, depending on what type of source you are choosing and whether it is connected to a AC bus or DC bus, and you have to choose the corresponding power electronics converters. So, like that is AC to DC, DC to DC, then again DC to AC is an inverter, or this is the back to back converter, that is AC to DC again AC. So, here just I am giving you the introduction as a black box, means it is giving okay, it is the supply is DC, it is again it is as it is connected to the AC bus. So, it is the DC to AC means inverter. If it is the supply is AC and I am supplying to the means connecting to the DC bus, so DC AC to DC converter, like that. But what is there, the configuration wise we will see later. So, this is the how to choose the this what are the different possibilities already I have shown there, but in a better way I want to explain. So, the sources which is connected to the AC bus, the all the renewable energy sources shown here, the storage are shown, the storage the battery storage is shown here, and the this is the domestic load, that is the smart household appliances, and the EV which is connected to the corresponding AC bus. That is possibility I have shown the example as for a AC bus, and also it is possible that we can connect it to DC bus. So, for the as we are connecting it to this AC bus, and how to choose the corresponding power electronics converter. So, as for the first case solar, the output is DC we know. So, we are choosing a DC to AC power electronics converter to interface to the AC grid. Similarly, for the wind power, the output is AC and we are connecting to AC. So, here it is directly shown AC to AC converter, but normally it is through a 2 stage conversion, that is AC to DC again AC. In the previous slide also I have shown like that. Okay. And when I am interfacing a storage, the storage there has to be bidirectional power flow, means the storage will be supplying to the bus when we have load is more, means and generation is less, and the storage is charging, means it is storing when there is a more generation is more. So, that is we need a bidirectional power electronics converter here, but that is as it is connected to AC bus. So, we are choosing a DC to AC converter. So, basically I will be focusing on this bidirectional means the power electronics converter for battery energy storage system in my next lecture in detail, the corresponding design and all. And then coming to the residential load or the whether it is a EV load, we will choose the corresponding power electronics source converters, like the our nowadays household appliances are all are smart in nature. So, we need AC to DC again AC to AC. Okay. So, that is a 2 stage conversion. So, as all the appliances are smart in nature. So, that is the inverter based AC inverter based the washing machines we are getting nowadays. So, we need a 2-stage power electronics converter here. So, which is connected to the AC bus, and the last one is the EV load, which is we are supplying from the AC, okay, and this EV for the charging purpose. So, EV will be the battery, EV battery will be charged by using a, so first we are converting AC to DC, then the EV is charged through using a DC to DC power electronics converter. So, this is about, this is one example. So, same thing you can draw for a DC bus system. So, how to choose the corresponding power electronics converter type, means type wise, whether it is DC to DC, again same thing if I am drawing for a DC bus. So, this will be DC to DC converter. Okay. So, now coming to the other part of the components of the microgrid. So, that is the different local power generating units, which I have shown as a renewable energy sources, but in another form we can define it as non-dispatchable and dispatchable. So, what do you mean by this non-dispatchable source? So, all the sources, that is the, you can say it is the renewable energy sources only, these RESs are coming under this non-dispatchable. Why? Because it cannot be controlled by the grid operators. So, because as you know, this renewable energy sources are weather dependent, it is diurnal in nature. So, we have no control over it. Okay. So, these are intermittent, these are the problems with the renewable energy sources. So, the sources are already you know wind, PV, hydro, biomass, all we have discussed, but the this new, the term used for it is the non-dispatchable power generating, means sources of energy, and which one is called dispatchable, which we can, means as when we need, depending on our load requirement, we can make it on or off. Okay. So, that is called dispatchable source of energy. Can anyone tell this is what is the dispatchable? That is the diesel generator is one example of the this dispatchable source of energy. Okay. So, here in this table I have just given the examples of this different local generating units of microgrid, where I have shown this solar, wind, mini hydro, here also I have mentioned the corresponding what is the availability. So, the solar is available only during day. So, it is diurnal in nature, and this wind and mini hydro are based on the geographical locations, the availability of the source, and whereas the diesel generator, which is means shown here, this is the dispatchable source of energy, whereas this all three renewable energy sources are coming under non-dispatchable source of energy. Okay. So, here I have shown the source, the corresponding control, whether it can be controlled, then it is dispatchable. If it cannot be controlled, it is non-dispatchable. Then the availability also it is mentioned, and the diesel generator, as it is it can be controlled, it is available any time or all the time, you can say, and the output of this corresponding local generating units. So, for solar PV already we know it is DC, it gives DC output. Similarly, for wind energy and micro hydro or the mini hydro, so we get it gives a AC output, and the diesel generator is also giving AC output. Okay. So, this is based on the source, availability, power output, the control, and corresponding power electronics interface. So, power electronics interface, if I will say, so if it is connected to the DC bus, so DC output connected to DC bus, then DC to DC converter, DC output connected to AC bus, we need what, inverter. Similarly, when it is giving AC output and it is connected to DC bus, we need the control rectifier. We are connecting to the AC bus, then we need a inverter. Okay. So, sorry, here it is just opposite, just AC output. If we are connecting to DC bus, this is the control rectifier, this is AC output connected to AC bus. So, there will be a bidirectional or two stage converter, AC to DC, again AC, and similar is the case for this mini hydro, mini hydro and wind are almost having similar type of power electronics converters, and coming to the diesel generator we do not need any power electronics converter. So, this is about the local power generating units. I have given one overview of it, and now in our in the theme of the our topic main, that is the design of mini hydro power plant and its integration with DC microgrid. So, our focus is on DC microgrid. So, obviously, we will talk about the advantages of DC microgrid, why nowadays we are moving from AC microgrid. So, AC microgrid is already established one, in our power system is totally AC, and because of this renewables we are again moving towards the AC DC based systems from AC to. So, here I have shown a comparison between the AC microgrid and DC microgrid. So, here if you will see the integration with the renewable energy sources, and when we are going for the sources like PV and fuel cell which gives a DC output. So, and I am connecting it to the DC microgrid. So, we do not need any power electronics converter, whereas if I am connecting it to a AC microgrid we need a power electronics converter. So, this makes a, so there is a need of extra power electronics converter here, and then again if you are integrating the DC system to the ESS, means energy storage system, then we do not need the direct integration is possible, whereas for the AC microgrid direct integration is not possible. And again if you are supplying to the DC load, which are nowadays the DC loads are the LED, the Bill DC fan, those are coming as a DC load, the EV, okay, then directly we can integrate to the DC microgrid, whereas we need a power electronics converter extra for AC microgrid. So, these are the means here what I want to say, it is not that AC is not totally obsolete, AC is still existing and we cannot immediately replace AC system, but we are moving from, because of the obvious, these are the advantages for which we are moving from AC system to the DC systems. So, and also the problems with the AC systems are, it gives the power quality issues are present. Yes, it is present in case of AC system. Need for synchronization required in case of AC system. Frequency you have to maintain for AC system, whereas this power quality issue is absent in case of DC system. You do not need any synchronization and there is no frequency maintenance issue. And coming to the skin effect, yes, it is present in case of AC microgrid, whereas it is absent in case of DC microgrid. And but if we will see about the demerits of the drawbacks of the DC system, the protection is well established, fully explored, or the means it is fully developed. So, it is not expensive in case of AC, whereas there is no standard till now for DC based systems. So, it is still underdeveloped, and so when we need any protection it is still expensive, and that is the problem with the DC based system. So, for the AC systems the standard is already, it is proper standards are available, whereas for the DC few standards are available. Okay, it is still in research state and we need to explore more on it, and as it is a AC is already established system. So, we need initial investment is low, whereas for a DC based system initial investment is high. So, there are so many advantages, but few disadvantages, but because of all the advantages we are again, as we are moving from the fossil based system towards the renewable energy based systems, again we are preferring trying to go from the AC to DC based microgrids. Okay. So, this is about the advantages. Then there are certain, as already I mentioned, there are no proper standards, but what are the standards available, that I have tried to mention here. So, the standards potential voltage levels for a DC microgrid is, for a low voltage level it is less than 48 or equal to 48. We are mainly actually working in this till now. We have published many papers, means with wind PV based 48 volt LVDC microgrid system. Okay. So, this can be used for this low power applications having this automobiles, USBs, okay, and small, for the small houses, and for these fans and standalone loads we can go for this less than 48 volt system. and these are very safe for the as per the safety factor, because the voltage is low. So, we do not need any extra protection for it, and in the second stage the voltage level is between 48 to 100, where again it is for the low power applications, lighting, residential and telecommunication industry, for the standalone facilities. Okay. Here still it is, as it is within 100, we do not need any extra protection. Okay. And but the load we can go up to few kilowatt, not more than that. Low voltage again, because if we will go for the high power application, again current will be very high. So, there we need again the protection. So, till 100 volt for the 48 as well as 100 volt system, we do not need such proper protection, whereas when we are going beyond 100, that is 100 to 400 volt is one standard available, and 400 to 1500 is the second one. So, for this is the medium voltage, you can say for this microgrid application, not, but 400 volt is still, if you will see in power system, 400 volt is also low voltage system, but here I am saying with respect to DC. Okay, do not take it otherwise. So, this is normally used for residential and major applications such as data centers and industries, and when I am going beyond 100 and above 120 volt, okay, which is lethal, we need proper protection for it. Okay. So, beyond 100, 20 and up to 1500 we need protections, but the power level for this up to 400, the power level is 500 kilowatt, whereas for from 400 to 1500 volt system, the power level means power limitation is up to, we can go up to 10 megawatt, but with a proper protection system. The applications for 400 to 1500 volt are shipboard, aircraft transportation and traction, etc. Okay. So, where so these are the potential, means in the DC microgrid and the corresponding voltage levels, the standards available. Apart from this, there are few other voltage levels also available in literature, where you can see this is 120 volt, 200 volt DC microgrid, 210. So, this is not properly standardized, but it is reported in literature, that is 360, 400, again up to 700 volt. Okay. So, that I have marked here. So, this is I am talking about the from the microgrid, AC microgrid, DC microgrid, then I have discussed about the advantages of DC microgrid. Mostly I have focused, though I talked about the disadvantages of DC microgrid, and then what are the it is not having proper standard, but what are the still what are the basic voltage levels we are operating at. Okay. So, this is about the potential voltage level of the DC microgrid. So, this is the first part of the today's lecture, that is the overview of microgrid and the classification and all. In the second part, I will talk about the energy storage system and why it is needed. What is the necessity of energy storage system when I am going for a renewable energy based microgrid. So, when, because the, as already mentioned, the renewable energy are intermittent and unpredictable in nature. So, and why it is unpredictable and intermittent, because it is influenced by weather or due to the this PV as due to the diurnal variation. Okay. So, this renewable energy sources is unpredictable. So, if there is diurnal, means during night time, if there is no sun, so you cannot supply, you cannot shut down your power system or the whole system. So, you need something to supply to the load. So, that is why we need a storage. Okay. So, when there is no source or less amount of generation, we need a backup unit which can supply to the load, or when there is a excess generation, we also need to store it, and when there is less generation or no generation, we can supply back to the load. So, that is why that is the main role of the storage in case of the this renewable energy based system, or you can say it is in a microgrid application. So, then coming to the what are the standards, means different type of storage available. There are many storages on the, but broadly it is divided into 4 types, that is electrochemical energy storage, fluid storage, mechanical storage, electromagnetic storage. Okay. So, here this when I am means I am not going to discuss about this all three storages. I will mainly focus on the electrochemical, and that too under electrochemical energy storage I am will be talking about the mostly used storage, that is the battery energy storage system, and apart from that I will talk little bit about the supercapacitor also. So, then when I am using this energy storage for microgrid, what advantage it provides? It provides it can be used as a spinning reserve and can be used for energy management, okay, to accommodate this new renewable, or the if you are adding renewable energy sources to it. It gives higher efficiency as well as provides a better means economic in nature. It is cost effective, and it provides better power quality and improves the reliability of the system, okay, and also gives a better voltage and frequency regulation if you need to control the means this renewable energy in a smoother way. And the last point is it gives a better asset utilization of the generation as well as the transmission. So, these are the needs for which means the energy storage is required in microgrid applications. And in now when I am talking about the microgrid and the use of energy storage system here. So, it is basically based on the whether it is for high power requirement or for electricity spectrum, or for high energy requirement, high energy density means high energy applications. So, you have it is divided into three main categories, that is based for the high power applications, it is mainly used for power management, okay. And so, the time of the means for how long you need the storage. So, based on that means it is basically for the high power, the time requirement is second or less than that, for very fraction of second you are using this, and it is for the power management application. And when there is a bridge means there is a switching between the two sources, then the storage gives a backup. At that time the duration is between second to minutes, okay. For the electricity storage spectrum means for the bridging power application means when there is a switching from one source to the other. So, at that time this energy storage provide a backup, and the time duration is between the seconds to minutes, okay. You just see first one is for a very less time it is giving a backup, whereas the second application when there is a switching it gives a backup from between the seconds to minutes. And for the higher energy density means for the energy management applications it gives a backup for hours or in days also, okay. So, where your applications like PV wind power and when you are going for the energy management applications, okay. So, this is about the application of means specifically energy storage, how it is used in microgrid and for how long, okay. So, here you have three options for less than second, between seconds to minutes, and for some hours or some days, okay. Then as already I have mentioned, I will talk mainly about apart from all different type of energy storage, mechanical storage, electromagnetic storage, I am focusing on the electrochemical storage, which is very oldest technology, okay. And among that you know this commonly used storage is the battery mostly used, and then now supercapacitor is also coming into picture, okay. So, between this battery and supercapacitor, this has two features means complementary characteristics. Battery gives a low specific power, high specific energy, less life cycle and less capacity of self discharge, okay. So, correspondingly less cost per watt hour, whereas the supercapacitor gives a less specific energy. So, that means battery is having high energy density, whereas supercapacitor is having high power density. Less specific energy, more specific power, fast charging, and but it gives a longer life. This is a less life cycle, okay, and high self discharge rate. So, that is why means why I want to focus on this. These two type of storage which is giving a complementary characteristics can be used together. So, that means for a longer duration we can use battery means forming this, if I am using battery and supercapacitor together. So, it forms a hybrid energy storage system. Okay. So, the use of supercapacitor is for a shorter duration, that is for the transient operation. So, we can improve the battery life. For steady state operation we will be using batteries, and for transient operation we can choose supercapacitor. Okay. So, that is the combination of, so nowadays battery supercapacitor combination is also giving a very better option for this microgrid applications. And we are also working on this hybrid energy storage, hybrid energy renewable sources as well as storage. So, and different type of batteries that are available here till now is lead acid, lithium ion, nickel cadmium, and the VRVs, and also sodium based batteries are also coming up, which I am not much aware also, but just standards are lead acid, lithium ion are mostly used. Okay. And I am not going about to discuss about the type of batteries or the chemical properties of it. I will talk about the sizing analysis of it, that I will cover in the next slide. Okay. So, sizing means, as we are talking about the batteries, means the energy storage, its uses and why it is important. Then when I am going for a renewable energy based microgrid, I need to design the, means take the, what should be the size of the battery, how much long it can give a backup for the system. So, for that, so there are I will take two examples. One is first for a standalone PV system. Okay. Battery sizing for a standalone PV system, and battery that will be used for a DC microgrid. Okay. So, but that is both are for the standalone only, but it is for a load, and this is in the first case I will talk about the whole system, not only the battery sizing, the complete a simple example, very simple example I will tell here. The each component of the standalone system will design. Okay. Then I will give one assignment on that, then I will go to the sizing of the battery for a DC microgrid application. So, these two things are left, so that I will discuss now. So, coming to the design of the complete standalone PV system. So, where each is having a component like the PV array, the charge control, means it is having the, if the standalone PV system is supplying a DC load, it is through a charge controller. Okay. And if the PV, means if there is more the generation is more, it is we need a storage, so which is charging and discharging depending on the load. And if you want to supply AC load in the household, you want to supply, we need a power electronics. This is a simple example. So, battery through, means the battery is supplying to the AC load through the inverter. So, the components are the power electronics converter, are the charge controller and inverter, and the you can design the system for the AC load or DC load. Okay. And here each component we need to do the sizing analysis, means decide the specification for how much load, what should be the size of the PV array, what should be the size of the battery, what should be the size of the specification of the power electronics component used here. Okay. So, let us take one example. So, before going to the example, first we will see the design steps. Okay. So, to depending on which type of system you are going to supply, if you are going for a DC supply, means you have to first calculate the load. Here I have mentioned for a AC system, means the system is completely, means having the PV array, charge controller, battery, inverter and AC load, this. Okay. So, this part I am supplying. So, I have this 5 components, and for that first you have to decide for what is the load of that household. Okay. So, you have to prepare a AC load chart, first step. Okay. And you have to correspondingly calculate the energy means how much energy is required to supply that power. You will calculate the total power requirement. Okay. That is the, by preparing the AC load chart, then calculate the corresponding energy estimation in watt hour. Okay. Load in watt and energy in watt hour. In the second step, you have to determine the size of the size and choice of the power electronics components. The power electronics components I have shown as it is supplying to the AC load. So, it is a charge controller as well as what we have the inverter here. So, the power rating, the voltage rating, voltage and current rating of the input and output of the inverter and the charge controller will decide, that is the inverter and charge controller selection in the second stage. In the third stage, we will do the main thing, that is the determination of the size of the battery, okay. And in the fourth stage, we will determine what is the PV module size required, so that it can supply that amount of the load. Okay. So, this is the third step is the battery sizing, and in the fourth stage we will do the solar PV sizing. So, that I will be explaining with the help of a simple problem. So, here the problem is, so design a PV system for a factory which contains 1 HP motor operating for 4 hours a day, 8 tube lights each of 40 watt operating for 7 hours a day, 3 fans of 60 watt each running for 6 hours a day. Consider a 1 day autonomy of battery. So, I will come to this part later. First, in the design step what I told, you have to prepare a AC load chart and correspondingly estimate the energy in watt hour. So, first we will make a table considering all the appliances here 1, 2, 3 we have one motor, okay, tube light and fan, corresponding power ratings are given in this. So, that is the motor is consuming means 1 HP power, that is 746 watt, the number 1 number, and tube light 40 consuming 80 watt and it is run 18 numbers, and per day it is running for 7 hours. Similarly, the motor is used for 4 hours a day, and the fan which we have 3 number of fans. So, and it is used for 6 hours a day. So, correspondingly from each component power appliances, we can calculate the corresponding wattage requirement. So, tube light 40 watt each, 18 numbers, so 320 watt. Similarly, fan 60 watt each, 3 numbers, so 180 watt. So, total wattage requirement or the load requirement is 1246 watt if you add up. So, that is the AC load chart we have prepared, and it is used for how many hours per day. So, the motor is used for 4 hours a day, the tube light is used 7 hours and the fans are used for 6 hours. So, correspondingly by the power into the number of hours, the energy required per day in watt hour is calculated to like this, just power into the corresponding number of hours. So, total energy requirement is calculated to be, means if you add up, so it gives us 6304 watt hour of energy. So, that is the we have prepared the load chart and correspondingly calculate the energy requirement for the household. Okay. So, in the second step we have to calculate or the design the power electronics components which are the inverter, and the second one is the charge controller. So, first if you will see the inverter, so the total wattage requirement is the power requirement is 1246, that is the output, and the output energy requirement is 6304 watt hour. So, if you will assume efficiency of the inverter, so this is a design problem. So, we can assume it is let us take it is greater than 90. So, it can vary from, you can take as per your design 92%, 96%. So, here I have taken 93% for the inverter efficiency. So, output, and here this is the output power, and so correspondingly what will be the input, that is the output by the efficiency. We are calculating the input power requirement. So, it is in volt ampere, that is the rating of the inverter. So, inverter capacity power rating is 1340 volt ampere, and total input energy is this 6304 divided by 0.93. So, that gives the total input energy for the inverter. So, this is how we are deciding the inverter capacity. Then coming to the charge controller selection. So, we have to first assume a system voltage. So, for this problem we have taken a system voltage of 24 volt. You can do your system design also, taking a example, let us take 12 volt or 48 volt system. So, here I have taken a 24 volt system. So, we are fixing the voltage by choosing the voltage of the system. So, from here we have mentioned the total watt hour energy requirement, that is the input of the inverter, and this is the wattage requirement of the inverter, and we have fixed the voltage, system voltage. So, what is the charge controller current rating? The power divided by the voltage will give you the charge controller. You can calculate, recalculate it whether I have done any mistake or not. So, you can see this is the charge controller specification, this is the energy requirement, power requirement, we have fixed, assumed the voltage. So, correspondingly we have calculated the current rating of the charge controller. Then in the our main goal is to decide the size of the battery, okay. And in the question if you see, I have consider 1 day autonomy. It may not be, it can be a 0 day autonomy or 1 day autonomy or 2 day autonomy, it is possible, but what is the meaning of this autonomy? First you need to understand. So, autonomy means the battery should be capable of supplying those many number of cloudy days. Okay. So, if the number of 1 day autonomy means the battery should be capable of, normally if 0 autonomy, the battery should be capable of supplying for 24 hours, whereas for 1 day autonomy it should be capable of 24 plus 1 more day. So, 48 hours backup it should be able to give. Similarly, if it is 2 days of autonomy, so 48 plus 24 again. So, like that you can calculate the size of the battery. So, coming to the battery sizing, so this number of days of autonomy is a very important term you need to understand. And then coming to the depth of discharge, what do you mean by DOD of the battery? Depth of discharge, it indicates how much of the total charge of the battery can be used, means we cannot discharge the battery below 50%. Okay. So, the depth of discharge of the battery, it may be given, but that is a standard. You can take when you are doing this design problem, you can assume a DOD of 50%. So, from the energy requirement, what is our we have calculated the total energy required 6780 watt hour. So, considering the 2 days means 1 day autonomy. So, it should be able to, means the size of the battery should be double of that. Okay. So, 1 day autonomy, so it should be able to supply for 48 hours. So, that is why the watt in the calculating the watt hour requirement, the watt hour, it is the actual calculated energy into twice of that, that is due to the autonomy. And as we have fixed the voltage, again it is mentioned here 24 volt. So, what will be the ampere hour rating of the battery? So, that watt hour divided by the voltage will give you the ampere hour rating. And again, as you cannot discharge the battery below 50%. So, considering the DOD of the battery 50%, the actual capacity of battery should be this 565 ampere hour divided by 0.5 will give you the actual ampere hour capacity of the battery. So, this is when you are trying to design the size of the battery for to supply the household having these many loads, and you have to make a battery sizing. So, you are not going to make your own battery, right? You have to choose from get it from the market. So, you can standard batteries are of different ampere hour rating. So, for this example I have chosen 112 volt 150 ampere hour. You can take your own battery 100 ampere hour also. So, for 12 volt 150 ampere hour battery, so you need to have the your system voltage is fixed at 24 volt. Okay. So, the number of batteries need to be connected in series is 24 by 12. So, 2 batteries you need to put in series because it is of 12 volt each, and as the capacity, actual capacity of the battery is calculated to be 1130 ampere hour. So, the number of batteries need to be connected in parallel is, each battery is of 150 ampere hour. So, 1130 by 150 it is nearly 8 batteries need to be connected in parallel. So, this is the sizing of the battery. So, all of you please note it down. After the end of this, if you have any doubt, I will clarify it. So, after this sizing of the battery, we will go to the next last part of the sizing, that is the PV sizing, sizing of the PV system. So, we have calculated the in the energy calculation for the supplying that amount of load, we need 6780 watt hour, okay. And the battery considering because the PV is supplying to the charge controller and it is charging the battery, then so there is a coming of battery efficiency. So, how much energy should come from the PV module? You can assume, this is the assumption only, 95% I have taken, you can take your own value 90 means greater than 90, 92% also you can do your calculation. So, these numbers will vary. So, considering that the energy required from the PV module is calculated to be 7140 watt hour. Okay. So, for this watt hour, so to calculate the wattage requirement of the PV system. So, how much means the sunshine hours, means for Indian scenario you have to take per day how many sunshine hours means sun is available. So, average it can vary between 5 to means 4 to 6 sunshine hours. So, here we have chosen a sunshine hour of 5 hours. So, watt hour divided by number of sunshine hour will give the PV module wattage, that is here it is calculated to be 1590, 7140 is the wattage required from the PV. Then the number of sunshine hours we have assumed it for the Indian scenario 4.5 hours, and the PV, so the PV module wattage rating required is 1590 watt. Okay. So, again, so as it is a total, so to supply that many loads, okay, so we need a PV module of this much wattage, but we cannot get a single PV module of this wattage rating. So, a standard PV module, there are different standards available. Here we have chosen a PV module of 150 watt 12 volt, okay, and the current rating is the PV current rating is 12.5 ampere. For this, so from this wattage rating and watt hour rating will decide the number of series and parallel connection. So, the system voltage is fixed for 24 volt. So, the PV module we have chosen the voltage is 12 volt. So, number of series connected PV modules are 24 by 12 is 2, and to decide the current rating, the ampere hour rating again for the PV module is 565 ampere hour, okay, and that previously we have calculated if you will see in the previous slide, and from by dividing by number of sunshine hours we are getting the total current rating. So, total current rating required by the need to supplied by the PV is 125.5, and so by taking a each PV module of 12.5 ampere size. So, total around 10.1 or this is giving a means as a whole taking a higher rating, we can go for a 11 number of PV modules need to be connected in parallel, and in the other way around from the this watt hour rating also dividing by the watt single PV module watt, we are getting the similar number 11. Total watt hour rating is 1590, and if you will divide it by 150 watt of single PV module. So, number of parallel connected PV modules are 11. So, this is the for a simple household appliances we are going to design a PV system, means having all its components. So, here I have covered all 4 components, means the 3 components basically the PV sizing, the battery sizing, then comes the power electronics component, under that the charge controller and inverter sizing. So, now I will give you this 2 assignments to solve. I will post these questions in the group, and for here also I will circulate. So, you can try it, and towards the end you have to submit these 2 assignments, same for one for the same AC load having different ratings, and for a DC load simple questions. Okay. So, try to solve it. Next is the, so this is a standalone PV system. Now, for a DC microgrid, when I am going to, so here I have not talked about the when I am interfacing with the DC bus, the battery is interfaced to the DC bus. So, we need a charging discharging, and it is interfaced to the DC bus through a bidirectional converter. Okay. So, this is the circuit. I am not going to talk anything about the circuit today, that a special class I will be taking on this. So, here this bidirectional converter, this design also will cover, but I am not talking anything about it, its operation. I am just saying how to choose the sizing of the battery when you are fixing the when you are designing the battery for a DC microgrid. So, here what is the means how you will decide? First is how much load you need to supply and for how long duration you need a backup. Okay. So, backup may need from means vary from few hours to few number of days also. So, for a here I will give a small example for 300 wattage of load and you are supplying and you are fixing the DC bus voltage to 48 volt, because we are designed our whole system during the power management also you will see the LVDC microgrid having a 48 volt LVDC microgrid. So, here we have tried to design the battery for to supply 300 wattage of load and the bus voltage is fixed to 48 volt. So, here how we will choose the battery rating or battery sizing. So, first is in the first step we have to calculate the battery current and then the ampere hour. Battery means you have to either means you have to give the voltage, current and the ampere hour capacity. Okay. So, based on the load already I have told it is a 300 watts. So, that is 0.3 kilowatt of load you are designing. Okay. And you have to assume the this DC-DC the bidirectional converter used here, which is interface between the DC microgrid and the battery. The efficiency of this is assumed to be 96%. Okay. And the battery voltage, so the bus voltage is 48 volt and battery voltage is fixed to 24 volt. Okay. So, as we are fixing the battery voltage and we will step it up or whatever the during buck operation also we can get it from 48 to 24. So, we are fixing the battery voltage to 24 volt. So, the current requirement of the battery is 12.5 ampere. Okay. So, what is the ampere hour capacity of the battery? So, ampere hour capacity of the battery will be decided by the current rating, battery current rating into the K factor, T factor. So, what is the K factor? It is the ratio between the rated capacity and ampere that can be supplied for the required time. Okay. And that will be given by the manufacturer. Okay. And the T factor is the temperature correction factor for ampere hour capacity, and it can be defined as the ratio of capacity at working temperature and standard capacity. Okay. Then the T factor, then the aging factor, then design margin and the overload factor. Okay. So, aging factor is to take the aging factor into consideration means it is normally multiplied by this is the IEEE standard, it is multiplied by 1.25 times, okay, considering the aging factor. So, it is the 25% extra we are taking, and this design margin normally there is a 5% extra we are taking a cushion of to consider it 5% extra we are taking. So, we are taking a oversize of 5%. So, it is multiplied by 1 that is 1.05, and similarly it can be overloaded to again 5%. So, further it is multiplied by 1.05. Okay. So, the current we have calculated 12.5. So, this K factor how we are getting, that is I will show you in the next slide. So, K factor is given by the provided by the manufacturer, and for different number of backup hours you have to choose it from this graph. Okay. So, here we have chosen for 2 hours backup, okay, and for 2 hour backup this and with this different number of volt per cell. So, for 1.75 volt per cell and for 2 hours backup this K factor is found to be 2.61. Okay. So, this actually this will be we will be getting from the battery manufacturer. So, from there this ampere hour capacity is the current rating into the K factor is 2.61 into the T factor, that is 25% extra, that is IEEE recommended considering the aging factor, that is 1.25 into the this design margin of 1.05 and the overload factor. So, the battery capacity is found to be 44.78 ampere hour. That means when we are going for a particular load based means household application we are doing like this, and for a this DC microgrid when we are going. So, when we are trying to put this is the 44 ampere hour 44.78 means nearly 45 ampere hour battery, but in standard whatever standards are available in the market, we have 42 ampere hour, then 65 ampere hour of battery. So, that is why for this is a actual design we have used in our lab, that I have shown here. So, that it will be useful while we will be going to the lab sessions. So, this we can go for 65 ampere hour, but it is much higher means so that is why we have chosen this 42 ampere hour of battery for our system. Okay. So, with this I will conclude my today's session. So, these are some of the references and the questions I have shown for the assignment I will share in the group. Okay, thank you all.